titration procedure starts on page 57 of your lab manual. I just want to save you some time. Remember, all pre-lab questions need to be attempted to get in the door and have that procedure. Of course, you would want to correct pre-lab questions before you turn in your lab report. But for the post-lab, you're skipping the first 4, meaning 1 through 4 for your post-lab questions can be skipped, because that has to do with the first part of the experiment that you didn't do, or would not have done. Quiz 6, I'll have a better idea on Wednesday. We're kind of in a routine now. We'll bring it up Wednesday. We'll talk about that then. But I can almost guarantee you there's going to be precipitation, acid base, and maybe something from today and Wednesday's lecture on there. Exam 2, Thursday 23rd, 5:30 p.m., 60 minutes. Lab 162, 3.6 through, it's usually 5.4, 5.5. Give you a bit better idea. We are on track as far as lecture by lecture with past semesters, so it should be right around there. And you can see that I have a science and lecture activity problems that's actually for the end of acid base. We have a little bit to talk about, but those are actually starting on the page that we're starting on. I didn't assign anything yet for the next sections. It depends how far we get. So we might come to one of those, which case I'll add to the list. I did add some new Moodle questions that do have to do with what we're talking about today. Anything you thought of now or over the weekend you want to ask? Good? All right. I hope you saw I did get the CSI extra credit in also. I'm not the one who tallies that. I just get a spreadsheet, so if you think there's a mistake, just let me know. Not a big deal. So we're going to pick up kind of where we left off. We had gone through our strong acid, strong base, our weak acid, strong base, and our strong acid, weak base combinations. Then I said we're going to talk about some things that don't like to follow the rules because nature does not like to categorize. Please note what we're going to be talking about on page 120, excluding the lecture activity question, the top part, is not really testable material. I'm not going to take you out of your comfort zone of these 3 things for acid base. But are these always going to result in all species in solution? So far, the ones we've looked at were all homogeneous mixtures, right? When we did the particle diagram, the ions and whatnot were floating around in the solution. What do you think is going to happen when we combine sulfuric acid and barium hydroxide? When we do our ion exchange, and I'll have a sheet in just a second, when we do our ion exchange, we will get a precipitate. Actually, it just looks weird to me, so I'm going to put that in the center for right now also. I don't want you guys to be at a disadvantage more than you already are. Come on. There it goes. So we can get a precipitate formed through an acid-base interaction, in which case it's both a precipitation reaction and it's an acid-base reaction. But again, for testing purposes, you should not expect to be encountered with something that gives you a precipitate, meaning if you think you got something that's insoluble for your ionic product, maybe double check your solubility table to make sure. So we get this idea, meaning we can have a precipitate that is totally valid. The next example is with baking soda, sodium bicarbonate, and vinegar, acetic acid. Has anybody made or seen the volcano experiment? Yeah, we're usually very familiar with that. Sodium bicarbonate is a base. Vinegar, acetic acid, is an acid. So it is an acid-base reaction, but it's actually very complex. And we can see here that we're going to eventually generate a gas through the secondary reaction to get that lava coming out of your volcano. But again, our vinegar, our sodium bicarbonate, our baking soda, acid-base interaction, ion exchange gives us our sodium acetate, but the other ion exchange gives us another acid. It gives us carbonic acid, which can further decompose, as we see in the second reaction, to produce that gas that causes your lava to come out of your volcano. Again, don't expect to see anything that complex, but we're just trying to show you that nature does what it wants, and we try to categorize it to help understand it, but there's always things that don't fit in the categories. Any questions? Would have been nice to get that done on Friday, but I didn't want to rush through those neutralization reactions, and you guys have a lot of good questions. In the other lecture, we actually did do this on Friday, because they didn't ask as many questions. Are we good? Meaning, from 23, the whole next page, and then on to the next page, 229, are on that lecture activity list. Meaning, we're going to start 4.4, another type of reaction. Now my sheet's going to come into place, so I can put the dot camera back in the middle. Won't be a lot on the slides. Most of it's just repeating what you have in your pages. Come on, there we go. A little high. Okay, so as we can see on number 1, page 124, we're moving into section 4.4, oxidation reduction reactions, more commonly just called redox. That's why I wrote redox up there. Notice acid-base reactions, we were watching the hydrogen ion move, right? The acid was the hydrogen ion donor, the base was the hydrogen ion acceptor. We really had to understand that to really see how the strong acid-weak base reaction worked. Redox reactions are electron transfer reactions. Now we have to watch electrons. They are formed through 2 different processes. As we can see, I have written oxidation and reduction. But before that, how will we be able to identify the difference between acid-base and redox? Well, if we see charges change, like the formation of an ion, or an ion turning into an atom, then there are moving electrons around. You can see that one process results in the loss of electrons, and the other process results in the gain of electrons. 2 processes put together is the oxidation reduction reaction, or redox. Any questions about number 1? I leave part B until we have the image that goes along with it, kind of on the next page, so don't worry, we'll talk about what we expect to see at the particle level. You have the table at number 2, which does also include the definition of oxidation and reduction. I put it in short terms, but the process of losing electrons is the same as saying the loss of electrons, or the process of gaining electrons is the same as saying the gaining of electrons. They do have an example half reaction. This is a process, the reaction goes with it, which would be titled an oxidation reaction or a reduction reaction, as we have typed out for us. The example, we take an atom, we create a cation. Well, to balance for charge, we have to have an electron there, right? That electron was removed from the atom to create the cation. If we're thinking about reduction, we're adding an electron to an atom, therefore we'd be creating an anion. X plus an electron would make X minus. Please note, although we will often write these processes separately, everything's going on at the same time, so therefore the oxidation reaction and the reduction reaction are both occurring simultaneously, and one would not occur without the other. They're what we call coupled reactions. They have to be occurring together. There's no reason to lose an electron unless there's something else nearby who wants to take the electron. Questions? The first of many terms. And I know I verbalized, I didn't write. You have a little place in your table. Remember the oxidation process, we're creating a cation. The reduction process, we're creating an anion. We're going to actually go through this with a specific example on the next page. Make sure I'm not missing any hands. So this is the table that you have on the next page. Again, like I said, most of the stuff that's in the slides you have in front of you. So we're considering these definitions at the particle level and symbolically for the formation of sodium chloride from sodium and chlorine. We're going to show the half reactions. We're going to identify which species is being oxidized, losing electrons, which species is being reduced, gaining electrons, and we're going to show the transfer of electrons from where they're produced to where they're consumed. We also have to make sure to conserve our electrons. If we produce a certain number of electrons, we have to use those. Or if we need to use a certain number, we have to produce those. So they have that set up. I'm going to move my paper up. Oxidation's on top. I'm just going to do oxy. You can use my shorthand. Reduction is red for oxidation reduction. I'll make sure I'm centered in just a second. There we go. I wanted to keep, I wrote the terms a little too high. We'll remind you in case you forget. So, when we're forming sodium chloride, and oxidation is the creation of a cation, which do you think is going to be oxidized, the sodium or the chlorine? Did I hear sodium? The sodium is the cation in sodium chloride. So for our oxidation, we're going to be dealing with the sodium. So symbolically, we have a sodium atom going to a sodium cation plus an electron. On the particle level, I'm just going to use a filled-in circle for my sodium. Atom is going to go to this filled-in circle but now have a charge plus a little electron. give you a place to write what is oxidized. Was the electron produced or consumed? It was produced. Because the sodium lost an electron, now we have an electron that we can use. So the electron is produced. Very important, it's a product. The product is then available, okay? Our acids, right? When we looked at their partial or complete ionization, the H plus was a product, so it could be used by the base. It is not right to write, it's not correct to write Na minus electron gives you Na plus, because then it would be on the reactant side. You want it on the product side. Since we know the chloride is the anion, and if the simplest form reduction produces anions, we're going to use our chlorine down here. Now, symbolically, we know chlorine is diatomic. There's two of those there, meaning we're going to make two Cl minuses. How many electrons would I need to do that? 2 electrons. Good. Bless you. If anything you get from 2 negative charges here, and have to have 2 negative charges there, balancing for charge. Or, we need to give each of the chlorine atoms an electron. Before we go on to the particle representation, are we producing the number of electrons that we need? Sorry, question.
I have a question for the oxidation.
Uh-huh.
Are we looking at this as Na plus an electron gives us stable Na?
No. Sodium is going to the sodium cation and the electron.
So stable,
The way that you worded it was backwards.
we're looking at it as stable sodium changing into a ion itself.
Actually, the ion is more stable. Okay?
I don't even know what this is.
That's all right. That's periodic trends or electron configurations later on in the semester. Anybody else? My question before. Oh, thank you. Yes.
I have a question about,
Mm-hmm.
say that, like, are we talking from reaction it's being produced? or
Yeah.
like-
Right here, it's a product being produced.
It's just the product of.
Yes. Yes. So just wording, sorry.
Yeah.
It's all right. So back to my question. Yes?
I think I mixed up with stable with neutral.
Okay, that's a big difference.
Yeah, so a neutral
We're
and.
taking a neutral atom, we're creating a cation and an electron, yes.
I was mixed up with words.
Wording too.
Makes more
That's all right.
sense. Yeah.
Anybody else? Okay. Did we produce enough electrons in the oxidation step for the reduction step? We need 2 down here, right? We only produce 1. So we're going to need 2 sodium atoms to make 2 sodium cations to get 2 electrons. So I'm going to fix my particle representation as well. Because we need to produce the number of electrons that we need. And for the diatomic chlorine, we need 2 electrons. I'll do the particle representation first. This is what they mean by conserving the electrons. We have to have the right numbers for both steps. As far as our particle representation, with the diatomic chlorine, we have 2 little electrons hanging around. We end up getting monoatomic chlorides. Since we added electrons to chlorine, chlorine is reduced. Give you a little line again. And electrons are consumed. And since we pluralized electrons up here, it just doesn't make any more sense. So electrons up there were produced. Because now we have 2. Consumed just meaning it's a reactant being added to the other reactant. I think the wording issues. As far as the whole process, the overall balanced chemical equation symbolically to make something that might think of being as simple as sodium chloride, we're taking 2 sodiums, that would be solid, this is just my work, plus once they interact. Don't worry too much about the middle. I added the middle over the years because if I leave it out, students get confused. Where are the ions? The ions are in that ionic formula. So I'm just trying to cover everybody's thinking styles. We'll actually talk a lot more about that process in chapter 9. Any questions? Yes?
Why is it gas in the middle?
Just because I know the whole process.
Okay, we don't have to worry
That's why I
about
said, don't worry. If I leave this out, some get confused. If I put it in, some get confused. Either way, somebody's gonna be confused. This is actually the true process, and when we get to chapter 9, you'll actually see why I wrote gas. If you remember, I did that even. Okay? It's just to be correct, that's all. You guys won't have to do that. Remember in part B in the little page, I said, oh, I'm waiting on that to get to a picture. We would expect to see electrons on the particle level. We drew them on the particle level. You also have this image on page 125. However, often they're left out because think of the size difference between an atom or an ion and an electron. Electrons are so small, and to preserve scale, authors often won't show them. However, why do we know that this is a redox reaction, the formation of magnesium oxide? We have neutral things going to things with charges. Electrons had to have been transferred. Magnesium atom to become a magnesium 2+, had to have lost 2 electrons. Each oxygen in the diatomic had to have gained 2 electrons to become O2-. So because we're seeing charges changing, that's another way of identifying that this is redox. Questions? Yes?
We're talking about transferring electrons. Like, is Na transferring from and to Cl that chlorine? Is it even exchange between them? I don't understand where they're coming.
The electrons are being produced when the cation is formed. We have the cation, we had to have lost an electron. How do we get the charge?
So are they giving it to one another?
Basically, yes.
Okay.
It's an exchange of electrons. It's happening very closely on the particle level. That's why I said it's not this happens and then that. It all happens at the same time. We separate it to make it more sensitive. Okay? Because if I wrote everything happening at the same time, it'd be like, what's that? Okay? Anybody else? It actually brings that idea up at the bottom of the page. I'll skip the first sentence. It says, we write them in half reactions to keep track of them being the electrons. But this is a convention for us rather than the representation of what's actually happening. So that kind of goes with your question. Okay, Austin? Good? You still look like you have a question.
I'm definitely going to be able to listen to some videos and so I understand the help on that.
Okay. Watch like it. All right. We have more terms coming up. On the next page, we have a little table at the top of the page. And I bumped this back up for the main terms of oxidation and reduction. When we're saying something's being oxidized and something's being reduced, we're talking about what happened to that thing. The sodium was oxidized, it lost an electron. The chlorine was reduced. Each chlorine atom gained an electron. Often we're not thinking about what's happening to that thing, we're thinking about what's causing that to happen. In which case we have 2 other terms. Oxidizing agent. The substance that causes oxidation by itself undergoing reduction. What caused the sodium to lose an electron? The presence of the chlorine gaining the electron. If the chlorine wouldn't have been there, it wouldn't have happened. So that means in our example, the chlorine for your table is the oxidizing agent. I put that too close, sorry. So for the sodium chloride example, diatomic chlorine is the oxidizing agent. Its presence causes the sodium atoms to lose electrons. The reducing agent is the substance that causes reduction by undergoing oxidation. What was oxidized? The sodium. If the sodium wouldn't have lost an electron, the chlorine couldn't have gained the electron. So our reducing agent is the sodium. I purposely used ever since. Agents are reagents, meaning they're reactants. They're like spies. They have to be there at the beginning to cause something to happen. If you ever ask what is the oxidizer reducing agent, multiple choice, never pick the products. It has to be a reactant. So think of it like a spy if you have to. It has to be there in place at the beginning in order to cause the process to happen. It has to be a reactant. Questions? You do have number 6. How do we determine what has gained or lost electrons? We look at the charge, right? We went to the sodium being oxidized because we knew it was going to be the cation. So it had to have lost electrons. We knew the chlorine is going to turn to the chloride because the chloride is the anion in sodium chloride. Sorry, sodium chloride. So we're watching changing charges. For practice, assign the charge of the ions in the compound below. Hopefully this is not hard as far as practice. So sodium sulfide, we know we have 2 sodium cations there. They're group 1, so therefore they're each plus 1. That means the sulfide must be 2 minus. In our calcium oxide, calcium group 2 is going to be plus 2. Therefore, the oxide has to be 2 minus to balance out that charge, or it's group 6, which is 2 minus. As far as iron 3 chloride, I know it's iron 3 because I know the chlorides are in group 7 and are minus 1. And there are 3 of them, therefore the iron must be plus 3. That's a transition, no. It's a transition metal, you don't have to memorize the charge, but we can figure the charge out. And then we have aluminum phosphide. Whichever way you like to do it, either group 5 is minus 3 or group 3 is plus 3. We know the aluminum is plus 3 and the phosphide has to be 3 minus. I want to give you an example of a redox reaction that's not in your lecture activity book because it helps you understand why we're going to do the next thing we're going to do. Make sure we're balanced. We have the carbon, we have 4 hydrogens. We need 2 up there to have 4 hydrogens. That gives us 2 oxygens and 2 oxygens. I need 2 over there for my oxygen. Although balance isn't important for the demonstration. That is a redox reaction. Combustion reactions are redox reactions. For our last example, we were able to kind of see what was happening because we had atoms turning to ions. There's no ions present, meaning we have to have a method to watch charges change when something doesn't have charges. I'm going to show you the charges for the elements within the compounds, and we're going to figure out what the carbons would be. So we would be going through these rules as to how I got those numbers, don't worry. But if, let's say CO2, if I have 2 oxygens that I'm saying are each minus 2, although they're not anions, it's not oxide, that would give me negative 4, right? Well, if it's a neutral compound, that means the carbon has to be plus 4. In the CH4, I have the hydrogens, each of them labeled as plus 1, but we have 4 of them. That means for neutral CH4, the carbon must be minus 4. And now we can see something has happened to carbon in order for the charges to change from negative 4 to plus 4. It lost electrons. We can also see that, wow, that diatomic, she wrote 0. We'll know why in a little bit. But over here, each of the oxygens goes into 0, they're minus 2. The oxygens gained electrons. The next thing we're doing is learning how to assign charges to things that aren't ionic. Because ionic is easy. When it's not ionic, it's hard. Any questions before we do that? And I'm hoping you're a little confused right now. It's good. Oxidation numbers also are referred to as oxidation states. If you ever looked up a table of the oxidation states for elements, there's one in your textbook in this section, you might say, wow, these things that I always thought just bound were molecular things like carbon actually can have these charges. This is the number of charges an atom would have in a molecule if the electrons were completely transferred. Meaning, I'm bringing stuff up that's farther in the semester, but it tends to help a little bit and you won't be tested on it. First off, we'll do a structure. Second off, electronegativity, which you might vaguely remember. Carbon is more electronegative than hydrogen. We will discuss it for testing purposes in chapter 9, but that means that the carbon is going to want the electrons. So we're going to have electrons being completely transferred per this theory to the carbon. And if I put 4 electrons on the carbon, I get -4. If I take an electron away from each hydrogen, I get +1. Just to help you understand how this theory works. The number of charges the atom would have in a molecule, not ionic compound, if the electrons were completely transferred. We're pretending they're ionic, even if they're not ionic. It's a way to see the movement of electrons by seeing charges change when there's no charges present, which is how we can now see something happen to carbon and something happen to the oxygen. The next steps is to go through the rules. Questions before we go through the rules? So for 7A, for monatomic species and free elements, I did add that to your electroactivity pages. I have a little thing here noted for myself. The oxidation state is equal to the charge of the species, which is how I said that O2 was 0 in that example. So if it's already ionic, why change the charge if we have a charge? Therefore, our sodium plus ion has a charge of +1, while its oxidation number would also be +1. No reason to change the charge when you have a charge. Therefore, diatomic chlorine, or diatomic oxygen in our last example, is neutral. Therefore, it has an oxidation number of 0 because it has 0 charge. An iron atom is neutral, the charge is 0, therefore the oxidation number is also 0. And the iron free ion has +3 charge, therefore its oxidation number is +3. That's not the reason for needing to learn how to do this. Those are the easy ones. It's things like that methane, or CH4, or the carbon dioxide, or the water, as far as things that don't have charges to why we need to learn this. Any questions? So if it's a monatomic atom, monatomic ion, or a free element, the charge is the same as the oxidation number. If it's a polyatomic species, we are assuming complete ionic character, kind of like the example I did with the CH4. Oxygen usually has an oxidation state of -2. Not always, and I will, maybe today, show you an example when it doesn't work that way. Halides, group 7, often have a -1 oxidation state, with fluorine always being -1. When a halide is combined with oxygen, the oxygen gets a -2. Therefore, the halide has to be positive. Hydrogen will have a +1 oxidation state, except with the metal, where it'll have a -1, meaning if a hydrogen is with a non-metal, it is +1. How I got the +1 for the CH4, the hydrogens. So let's just do a simple example. HClO. We know the hydrogen is going to be a +1 cation, because this is an acid, so if I put it in water, we're going to have some incomplete ionization of this, but that is going to be +1. Oxygen is usually -2 unless it doesn't work. Meaning, if this is a neutral compound, anybody figure out what the chlorine is going to be? Another +1. +1 + 1 -2 gives you 0. Your oxidation numbers have to add up to the charge on the species. And since this is a neutral compound, they have to go to 0. If we were doing this for a polyatomic ion, they'd have to add up to the charge on the ion itself. Let's do a polyatomic. How about chloride? So oxygen is usually -2. That's what I go to right away. So -2. That's on each of the oxygen atoms. So we have 3 of them. So -2 times 3 is -6. But I have to keep one of the negative charges for the charge of the species. Therefore, the chlorine will be +5. +5 - 6 gives me -1. Want to do another example? I think there's more in the next actual practice on the next page. Sorry, it's on the next page. It's just farther down. I don't know. I turned my page over. It's the next page. Sorry. Let's do one more, and then we'll go to page 127. Let's do hydrogen peroxide. Oxygen is usually -2 unless it doesn't work, right? So if I say that's -2, and there are 2 of them, that means it would have to be -4 overall. Both the hydrogens together would have to be +4. To get it per hydrogen, you would divide out, and you get +2. Is that possible? Hydrogen only has 1 electron. How could it be +2? It can't, you lose 2, right? Or hydrogen will have +1 oxidation state except with metals, in which case it's -1. This is an example of when using -2 for oxygen doesn't work. I said, oxygen is -2 unless it doesn't work. This doesn't work. It gives you an answer that does not make sense. In which case, go to the hydrogen rule. Am I applying that? Okay. Hydrogen +1, because it's with a non-metal. There are 2 of them, meaning it's +2 overall. That means both the oxygens together have to be -2. Divide that out, we get -1 for each oxygen. And that actually works. I'm going to put this on the center screen, just so you guys can see it better, because you don't have it in your actual pages. This is what I had slightly referred to earlier about a table, a periodic table with oxidation states on it. You can use this to check your work if you're doing practice at home. If you go over the oxygen, it's like, oh, okay, hey, look at that. It does work. -1 is possible. The ones in red are the most common. Yes, question? No. Use the rules to figure out what the numbers are. So no, it's not giving information on the exam. It's a when you're doing practice at home. See, hey, can my answer be right? However, if you look at the numbers in the groups, group 1, we don't see anything greater than +1. Group 2, nothing greater than +2. Group 3, nothing greater than +3. Group 4, the carbon group, nothing greater than +4. Group 5, the highest positive number is +5. So, if you kind of get to know it, you can say, hey, even on an exam, think, oh, I got a, I don't know, +6 oxidation state for nitrogen. Oh, wait, it's group 5. That's impossible. I made a mistake. That's wrong. And that's what they're kind of having you think about in part B of number 8. I did not address the things before that. I kind of started going on my own for a second there. So this is the oxidation numbers possible for various elements. Find some that are consistent with ionic charges you would predict. Metals, right? +1. Group 1. +2. Group 2. Even in group 3, aluminum +3. That makes sense. What are some that don't seem consistent with what you predict? Well, non-metals, you expect them to be anions, have negative charges, but we see positive oxidation numbers over here along with negatives. So that's something that's a little more unusual now. Any questions before we do some more practice? Yes? Well, it's practice and using the rules. So this is the main slide for rules, because that is, if it's a monatomic, the number equals the charge you already have. This is how you figure out things, and you use something you know per the rule. Oxygen is handy, or hydrogen, to find out what you don't know. So I don't like the word memorize. If you practice enough, you're not cramming it in your head. I can't hear you, sorry. It's just my ears. Yes, noble gases do form compounds. So the question was referring to, we have, actually there's 3, helium, neon, and argon. We have noble gases have an oxidation numbers. Yes, they do form compounds. But the ones at the top don't. Okay? We'll actually see some of those xenon compounds in chapters 9 and 10. Anybody else before we do some practice? The practice I want to do is number 9 on page 427. Get a clean sheet out so we're not distracted by other things. First one is potassium nitrate, and I'll put this in the center, don't worry. up, they have your potassium first, then they have the nitrogen and the oxygen. Please note the order that they have things lined up does not mean that's the order you have to do it in. But for this one, the potassium is the easiest because we know this is an ionic compound. We know potassium is group 1. So therefore, it's going to have the same charge as it would have its ionic charge. So its oxidation number is +1. Then sometimes it makes it a little easier to take off that ion because it's less stuff to look at. And everybody's different. Some people like to leave it all together. Some people like to take out the anion that we're working with now. Oxygen is usually -2 unless it doesn't work. Now we can figure out what the nitrogen is. If we have 3 oxygens which are each -2, that's -6. We have to keep one of the negative charges, so we're at -5. That means the nitrogen is +5. It is group 5, most positive oxidation number is +5, so it is valid. And doing this kind of thing is a bunch of the Moodles that I put on the list. Trying to get you to practice right away before Wednesday. What about H2SO4? We have our hydrogen, then the sulfur, and then the oxygen. Well, we know this is an acid. If we put it in water, we'll expect the hydrogens to be +1 ions, or hydrogens +1 unless it's with the metal. No metal's present, so it's still +1. Meaning we can take both of those guys off and just deal with the anion. Oxygen's -2 unless it doesn't work. -2. We have 4 of them, which altogether, actually I didn't write this before I just said it, gives us -8. We have to keep 2 of the negative charges, meaning we're needing to cancel out -6. Well, that means our sulfur is going to be +6. It's in group 6, +6 is valid. Any questions so far? What about FeCr2O7? Does anybody know what the charge is on Cr2O7? The dichromate. Because we have to know that charge in order with the charges on the iron. The iron can have more than one charged ion. What was that? -2 to here? Good job. So if this thing right here is -2, that means our iron has to be +2. Now we can take out the anion, Cr2O7, put its charge on to figure out the rest. So we're going to use a very simple method. Oxygen is -2 unless it doesn't work. If we have 7 oxygens that are each -2, that means overall we have -14. Yes?
What came away that CR2 and O7 is -2 together?
The polyatomic ion, we need to know the charge.
Oh,
Okay. Good. -14 overall, but we need to keep 2 of the negative charges, so we really need to cancel out -12. That means both chromiums put together are +12, but we need to assign oxidation numbers per atom, so we divide that out, and that gives us +6. Let's see if that's possible. Sorry. It's way over there. Sorry, you guys over there. Let's see if that's possible for chromium. Yes, we go all the way up to +6. So yes, it's good. So that's what I mean by you use that at home to check. See if you're doing things right. Okay. Aluminum phosphate is our next example. AlPO4. What's the charge on the aluminum cation? +3, group 3, right? So +3. That tells us that the phosphate is -3. And we're going to use the same idea. Oxygen is usually -2 unless it doesn't work. -2. Oh, grab the minus, there we go. 4 times 2 would give us overall -8, but we have to keep 3 of those negative charges, meaning we need to cancel out the -5. That tells us that the phosphorus is +5. When you're working with oxoanions, usually using the oxygen being -2, if it doesn't work, it's a really good place to start. The only way you know if it doesn't work is, did I get a charge or oxidation number for the other element that doesn't work per where it's located in the periodic table? Phosphorus is group 5, +5 works. What about H2? 0, remember? Monatomic species and free elements. Diatomic elements are free elements, so 0 for each hydrogen in the diatomic hydrogen. The last one we have is water. If you recall, when I started this topic with that reaction of the CH4 and the oxygen to produce carbon dioxide and water, we did have oxidation numbers put on of +1 and -2, and hopefully now let's make consensus of why I go +1 and -2. The hydrogen rule. Hydrogen is +1 unless it's with the metal. It has to be +1. There are 2 of them, which means we have to cancel out -2. That's right, we have to cancel out +2, which gives us -2. So I hope you're getting the idea, especially the person who asked the question earlier. This is not about memorizing things. It's about using the rules enough so it just becomes mental muscle memory. Does anybody know why chlorine is always -1? Just polling the audience. Yes, back there? That's exactly right. And it's not something I can ask on an exam until we get to that chapter, but I wanted to see if anybody knew. It's the most electronegative. I kind of gave you a taste of that with that CH4 example, and that's why it is only -1, whereas the other halides have all kinds of oxidation numbers. On Wednesday, we're going to be going through a bunch of reactions, meaning I really want you to practice these oxidation numbers before that because we're going to be using the oxidation numbers to figure out what happened, kind of like in our methane reaction. You can see, oh, the carbon went from -4 to +4. Electrons were transferred, or the oxygen went from 0 to -2s. We're going to be watching what happens to the oxidation number to figure out what happened. So at the bottom of page 127, they have a handy thing that I have a lot of students tell me they really like. So if the horizontal line is 0, we have positive up, negative down, and this is oxidation number. If our oxidation number goes down, meaning becomes either less positive or becomes negative, that is reduction. You're adding electrons which are negatively charged. If your oxidation number goes up, either becoming less negative or turning positive, well, you're removing electrons, you're removing negative charges. That's oxidation. And that would be really handy, because Wednesday's going to be doing go through a bunch of reactions, assigning our oxidation numbers, looking and seeing what changed and which way did it go. Did it become more positive? Did it become more negative? To finish out today, I'm going to put the screen in the middle again. I want to pause just for a second in case somebody's still needing this. If you do need it, remember I always have my stuff up here. You can always take a picture at the end. Because this is a summary of what we're doing on all of Wednesday, and it might trail into Friday. There are 1, 2, 3, 4, 5, 6 different types of reactions, and this is telling you what you would be responsible for the different types of reactions. You can see on Wednesday we're going to start with combination, decomposition, and combustion, and for those, you only need to be able to identify the element oxides, the element reduced, and the oxidizing agent along with the reducing agent. To be able to do that, though, you have to be able to assign the oxidation numbers. When it comes to the displacement reactions, which you might know as single displacement or single replacement, depending on textbooks, we have hydrogen, metal, and halogen displacement, and we can see for those, in addition to the element oxide is the element reduced, and those two agents, we're also going to be doing more. We're going to be writing half reactions, how to do the sodium chloride. We're going to be giving the overall reaction, meaning you have to know how to predict the products. We're going to predict if the reaction actually occurs using the activity series, something you may be familiar with. And we're going to need to be able to identify how many electrons were transferred. For example, sodium chloride example, that would have been 2, right? Each sodium atom lost 2 electrons, each chlorine atom gained 2 electrons, so 2 electrons were transferred. This is a good place to stop, even though we do have a minute, because I don't want to do a reaction and have you run out the door. So next time, if you have a